Well, okay, welcome everybody. This is week 5. We're getting close to being a third done with the semester, if you can believe that. The plan today is to wrap up the sampling chapter. And at the end of class last week, after I'd stopped recording, there were some questions about multi-channel expansion and PlayBuf, and I think I cooked up some sort of example off camera that was kind of interesting. So I just wanted to put this, on the video, on the lecture video. And so I've just kind of pulled some stuff from week 4's lecture code. So I have the, so I've saved this file as, I'm in my week 5 folder, and this is the file we're looking at. And then I've just copied the exact same folder of sounds into that same parent folder. So we're reading the buffer in, we just give it the server, and then only the, the folder in the same location followed by the name of the file itself, and then resolve relative, just to refresh everybody's memory, turns this into an absolute path. And this is what we need. So we have this, we can play it. Okay, so that's kind of nice. And then I have a synth def here, which does just very simple stuff. We have an argument for the buffer, and we're using PlayBuf to just play it back at the normal rate. The rate can be modified. We scale it down by a factor of 5. Turn this, just confirming this is in fact a one-channel file. So we just copy it to both channels and play it. And so just very simple. And I wanted to sort of play around with this synth def a little bit to kind of explore multi-channel expansion, mostly just to show that it just behaves exactly the same way it does with sampling UGens as it does with synthesis UGens. So what we might do here is, I don't know, we'll say sig is going to be 10.collect. I guess this is really more iteration. Let's do multi-channel expansion. Do something the same way. So we have this rate argument, but let's also continue scaling this PlayBuf by a random number between negative 12 and 0. By the way, this rand with a capital R is a UGen, and it really only runs at the initialization rate, but you can use the language side rrand here. The problem with that is that when you and we're going to do MIDI ratio here also. So this will just kind of return a random value every time we run it in the language, but when we bake it into a synth def, that random value gets called exactly once, becomes a permanent number, and so if we do this. Same thing. But if we change this to rand, this is now a UGen. So every time a synth is called, then we get a, right? And that's what we want here. So it's still just one random value that doesn't change, but every synth calls this random process. So we are going to say, let's do 12 of these. Another little thing that always kind of messes people up here is if we say, I want 12 of these random numbers, and then I want to convert them to MIDI ratios. There's an order of operations thing that happens here, and this is in chapter 1, I think, of the book, which is that methods take precedence over binary operators. And so we're actually trying to duplicate this rand by this number, which doesn't really make a lot of sense because you can't duplicate something a non-integer number of times. So you've got to either put this in parentheses, and that would work, or you can use the dupe method, which forces dupe to happen first and then MIDI ratio. So lots of little trip-ups here. So now, once we, at this point in the synth def, sig is a PlayBuf. It's got one channel. It's using this buffer. But then rate is actually an array of 12 random numbers, each of which is going to be between negative 12 and 0, converted to a ratio. So now sig is a 12-channel signal. 12 mono signals, and so we can say sig equals splay to basically mix that down to stereo and spread them across the stereo field. And at this point, we no longer really need this. I mean, splay is doing some sort of level compensation, and it's also producing a 2-channel signal. So I'm just going to go ahead and delete all of this. And now it sounds like this. We don't have a done action 2 here. And because now they're all different lengths, we can either do something fancy with detect silence, which I don't really want to get into right now, but if you do want to see what this process would look like for sort of done action 2ing at the correct moment, you can talk to me sort of outside of class. What we can do is just say, OK, the lowest possible number is going to be 12 semitones down, which is an octave. And so we just need some finite UGen with a done action 2 that is that long. So we'll just say this line goes from 0 to 0 over the duration of the buffer times 2, and it has done action 2. So this line isn't really integrated into the synthesis process other than to just have the done flag, which says, and everybody out, right? And so it's guaranteed to happen and won't cut off any of the sound. So we can then, actually, I still have one lingering, so let's clean up and then. So all the PlayBufs do their thing, and then after enough time has passed, line kicks in and does its thing. And one thing you can hear here is that they all start in phase, right? They're all starting at 0, at frame 0. And so there's kind of a smearing, I guess you'd call it like a sort of phasing effect, where they all kind of drift out of phase. Which is kind of cool. Maybe you like that. But something else we could do is have each one start at a random start position. And so again, we'll say rand between 0 and buff frames. And here we have to kind of do a little bit of manual work because we don't really want to start right at the end because loop is 0, and if something picks a starting frame too close to the end, we have nowhere to go. So we could turn looping on, but then we'd start back at the beginning of the sound, and maybe we don't want that. So I'm not really sure what to do. Maybe we can say we'll take the number of frames in the buffer and then scale it by 0.2. So we're just going to pick a random start somewhere in the first fifth of the sound file. And that seems OK. We are then going to dupe this by 12 as well. And so now no more phasing thing. We can make this really low and, I guess, increase this. Yeah, kind of like haunted dollhouse vibes or something. I don't know. So anyway, this is just multi-channel expansion. We take a mono UGen, it becomes an array of 12 mono UGens. If another argument is also expanding, those parameters will get dumped into the array as well. And then we just have to remember that we're working with a large multi-channel signal, but only working with 2 outputs, two hardware channels. So we've got to do something to condense with splay, or just summing and then duplicating by 2, whatever you like. But I think this all seems to make sense to people. Yeah. And so there's a lot of really, you can duplicate by 50 or 100, and SuperCollider will usually not balk at any of that, and it'll say, oh, sure, yeah, whatever. And you can make some really rich and dense sounds with not a lot of code, which is kind of nice. Question?
Please feel free to divert this question if this goes too far off topic, but is there any way to control the position of the individual channels in splay, or is it just width and center?
Good question. So the question is, the way splay handles its input array is that it will just take the 0th item, put it on the left, the last item, put it on the right, and linearly space the ones in between in the stereo field. And so if you wanted to, you can always do something like this, right? It's just an array. So you can just randomly reorder the channels. But here, it's pretty random anyway, so it doesn't really make a difference. But if you were doing a sort of, descending scale from left to right, then scramble would be useful here to just jumble them up. But to manually reorder them.
Well, and I guess I'm thinking more in terms of to be able to pan the individual elements around, like with an LF noise 1 or something.
Yeah, okay. Well, so if you wanted to take these 12 mono signals and then use a noise generator to pan each one of them in stereo, is that what you're saying? Yeah. So you could do that. You would follow up this, sig with a sig equals pan2.ar, sig LF noise, whatever, and then it would become, I think, an array containing 12 size 2 arrays, because each one of those is now a stereo signal. And so then I think you would do sum on the resulting array, which would sum all of those 2 size arrays together into one size 2 array, and that would be the sum of all of those randomly panned signals.
Is the sum, is that analogous to the like mix.new?
Yes. Okay. Yeah. If you have, well, you can't do it in the language, but yeah, mix is it's not even a UGen actually. It's I don't think. I mean the thing is, UGens are just signal generators, and a signal is just a bunch of numbers. So an array of numbers and an array of UGens is basically the same thing. Sig, mix.new and sum, those I think those are literally exactly the same operation.
Okay, cool.
Yeah.
Thank you.
Sure. Okay. Well, I'd like to move on from PlayBuf and talk about the other buffer reading UGen, which is BufRd. These are, functionally they do the same thing. They read a buffer, but they are by design different. PlayBuf has this kind of internal pointer, which is automatically advancing through whatever buffer it's given at a particular speed based on the rate argument. But in PlayBuf, we don't really have direct control over where that pointer is. We give it a speed and we say go, and off it goes, and we kind of have no control over it. And this is handy, if we don't want to have to think about it. If we just want to kind of do a one-shot sample, we just say just play, done action 2, off you go, right? And that's very easy. But sometimes we want to directly control the movement and speed of the pointer itself, and this is where BufRd it really shines. So BufRd doesn't play the buffer automatically. We need to say, here is your frame pointer. And it can be any audio rate signal, which is really exciting. So let me start by, I guess we can just reuse this fins file. And go ahead and build a very simple synth-def. Here's what BufRd expects. The first argument is just like PlayBuf. It just needs to know how many channels. So if it's a mono buffer, it's 1. If it's a stereo buffer, it's 2, etc. Fins was 1, and we're going to keep using that, so we'll just say 1 here. Then the buffer. So we'll do this thing again where we create an argument so that we can pass the buffer in when we call the synth. And then phase. This is the audio rate pointer. So what we need to do here is make another variable, and we need to provide an audio rate signal which is going to access frames in the buffer. And let's do something very simple and just read from beginning to end. And what we can actually do is just use our good friend line. This is a perfectly good option for this. So we want line must be audio rate. If we're producing an audio signal by reading into a buffer filled with audio samples, it's got to be audio rate. Line takes a start position, an end position, a duration, and a mul and add, and a done action. So we want to start at frame 0, and we want to go to the end of the buffer. How many frames are in this buffer? Well, we could say fins.numFrames -1, and that would give us the correct value, but we want to be flexible here. We want to use this buffer argument that we've defined, and so I believe I've showed these in class before, but just in case I didn't, or in case anyone has forgotten, if we go into the UGen category and go into buffer, are they in here? I think it's info, actually. Is there info? Yes, these are unit. Gosh, where are they? Maybe I can find them this way. Yeah, they are info UGens, but anyway, here's a good sort of look at what they are, right? You have buff channels, well, BufDur, buff channels, buff frames. These are just UGens which extract information from a buffer, but they're UGens. So you can deploy them in a synth-def. They can be run at the control rate just in case you swap one buffer for another. They'll track those changes. I often do IR. So anyway, we're going to say buff frames.ir buff. Technically, -1 is appropriate here because this is an index, and this is the index of the last frame in the buffer. I don't think you'll notice any sonic difference if you just forget to subtract 1. I don't think anything's going to blow up, but it's good to be precise. And then for the duration of the buffer, again, we can just use BufDur, right? This just grabs the duration. And then a done action too, because when the line is finished, we're at the end of the buffer, and we're done. I know, not a very exciting result. It's the exact same thing that PlayBuf did, but we have a lot more flexibility here. Usually the first question that comes up here is, how do you make it loop? And if you're using line, you can't. Line doesn't loop. We can't retrigger line. We can't make it go backwards. We can't make it reset. It's one of the simplest UGens. So if you wanted to make it loop, you got to use something different. And for that, what I usually recommend is phasor. So phasor is a resettable linear ramp that goes from a start to an end. It has a trigger input, so you can at any point tell it to go back to its start position. And you can also provide it with a rate value. And the rate is the amount of increment per sample. And I mean like per digital audio sample, like 48,000 of them per second. And if we are going to be reading through a buffer, then assuming sample rates are the same, we just want that rate to be 1, right? 1 sample per sample. Pretty simple. So let's do this. Phasor. First, we have a trigger. Now, phasor automatically starts, when you create. So we don't really need to trigger it initially. It's automatically triggered, but we can just let it loop. So we'll just say we're not going to retrigger this. We could if we want, but we're not going to. Just like with PlayBuf, if the buffer is at a sample rate that's different from the server, you do want to use buff rate scale to compensate for the mismatch. And I mean, you could put a rate argument here, I guess. Let's do that. And then we have the start position and the end position. And here we don't do -1 because this value determines the wrap point of phasor. It is the value when reached becomes 0. So phasor never actually outputs this value, which is why we make it buff frames. So if the buffer has 10 frames, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we would say this buffer has 10 frames. That's the endpoint, because when it gets to 10, it actually becomes 0 instead. So it never actually reaches this value. It just uses it as the wrap point. That's my understanding. So I think that's all we need to do here. Right. Goes back to the beginning. Yeah, so we have some aliasing here, so it gets really crunchy really fast. It's like zipping through this file, hundreds of times a second. But the same usual stuff works here, So rate adjustment, that's all pretty straightforward. There are some other options. I think phasor is kind of the most utility. It's really kind of designed for this kind of thing. Where you can trigger back to the start position, you can adjust the rate, you can adjust the start and end points. It's very, very flexible. But you can also use LF-SAW. This is technically a linear ramp oscillator. You can give it a frequency, but you need to do a little bit of math to make it behave like phasor. But you can also just kind of treat it more experimentally and just kind of see what happens. And there's also sweep. This is a triggerable linear ramp. You basically start it, and it counts up at a rate and never looks back until you re-trigger it, and then it'll start back at 0 again. So kind of different options, but they'll all work. But the really fun stuff, I think, is when you start using nonlinear pointers and start reading through the file kind of in strange ways. So let's do let's see. well, let's comment this out, and we'll say, let's see, the 1 over the duration of the buffer, right? Because the period of the sine wave is going to be the duration. So it'll take one full cycle to go forward and back through. Not too worried about what's happening here. But don't care about the phase so much. Although I guess we could do 3 pi over 2. This makes the sine wave start, 3/4 of the way through, so at its lowest point. So it'll actually start at 0. Right. Let me know if I'm going too fast here. So, this is the frequency of the sine wave, which is the reciprocal of the duration of the buffer. We're just adjusting the initial phase, so it starts at its minimum point, which is 0, and its highest point is the end of the buffer. So we're going to get something which sinusoidally goes from the beginning to the end, and then it will come back. And the length of that cycle will be the duration of the buffer, unless I've messed something up here. And then we can just put our rate argument kind of right here, just to scale the frequency of the sine wave. It's coming back. There it is. And then lots of fun stuff you can do with multi-channel expansion. Kind of do the same thing here. This is getting a little bit messy for my comfort zone, so I'll try to make it a little bit cleaner. I guess that'll do. So we're going to take the rate, and we're going to multiply it by... I actually have no idea what this is going to sound like. We're just doing the same thing we did earlier. Plug it in. And here we go. Pipe this into a feedback delay and some reverb, and you got yourself a composition. Yeah, and one thing I really love about SuperCollider in general is you have these functions, you create them, you play them, and then they just run. You can just add them and remove them, interact with the language dynamically, and it's really great. So that is a little multi-channel expansion, modulating the. Let's do one more thing. Just kind of bringing back our linear ramp. This back to this version here. Just our repeating phaser. You can then sort of further process the signal. Like we could add a little bit of noise to it, maybe. Like some linearly interpolated noise. And for the range, remember that the units here are samples. So we need to think in terms of we can convert or whatever. Let's say we wanted to kind of 8 times a second kind of pick a half a second here, half a second there. So we can say half a second, but then convert this to samples, which we do by multiplying by the sample rate. And there's a UGen called sample rate, which just returns the sample rate. So that's an option. So that'll sound. Let's see what that sounds like. It's kind of cool. Let's do this. So now we have with the linear interpolation, every segment has a fixed slope, right? So I think that's why it's just sort of basically changing the pitch. Sort of at a constant, so that every eighth of a second we have like a new transposition. But the quadratic interpolation will be kind of a zippier thing. And we can tweak these numbers till we like it. And let's go ahead and do this. Right? Right, so now each one is using this phasor, but then we have some noise messing with the exact position, blending them all together in stereo. And so we can still kind of hear the original sound. It's not quite so chaotic as before. Now. Okay, not bad. All right, so with the rest of our time today, I would like to move on to section 4.4, which is recording UGens. With PlayBuf, its companion is RecordBuf. I'm not going to cover RecordBuf today because that's in the homework and I'd like you to read the book. And also because we are currently on BufRead. So I think it makes sense to talk about its counterpart, which is BufWrite or BufWr, however you want to pronounce that. Right, so this is each one that reads from a buffer has a counterpart which writes to a buffer. And the design of PlayBuf and RecordBuf is very much the same, although I don't think you can adjust the rate. Yeah, it's got different arguments, but actually quite a few different arguments. But it does have loop and trigger and done action and buff num and things like that. So the RecordBuf is nice because overdubbing and mixing new content in is very easy with RecordBuf. I know I just said I wasn't going to talk about RecordBuf, but here we are. So record level is the level, a level scaler applied to the signal right before it comes in and is recorded. And pre-level is a scaler applied to the signal that is already recorded in the buffer. So basically you can freely mix between existing content and new content. And the defaults are 1 for the incoming signal and 0 for the existing signal, which means the default behavior is to overwrite old content, like magnetic tape. Right? You just record right over it, and it's gone forever. Right? But you can set this to be sort of 0.5 or like -3 .dB/amp, and that way the new content will be attenuated by a little bit, and then the new content will be old content attenuated, new content overdubbed, and this allows us to do fun things with like delays and accumulating textures and stuff like that. BufWrite is much more similarly designed to BufRead than RecordBuf and PlayBuf. We give it an input signal, the buffer to write into, and again an audio rate pointer which says where to record. Weird stuff happens if you give it nonlinear pointer because you start skipping over samples and overwriting samples, and so it gets pretty glitchy pretty quick. So unless you're like really into the glitch flavors, I generally recommend just using line or phasor to write into a buffer with BufRead. But everything's worth trying here. Yes.
Well, and kind of a question about that. We mentioned that for BufRead that like AR only. If you do KR, does it just play like a sample at the control rate, or does it actually fail?
I think it actually says this input must be audio rate. Okay. It won't play. Let's try it. Yeah, it doesn't like that. Okay. It says, yeah. Well, okay. So it complains about it in a weird way, I guess. No, sorry. I'm doing the wrong thing. This is what I meant to do. So now it says BufRead. Yeah. So it just refuses to play nice if you don't give it an audio rate.
Could like theoretically use like latch to downsample.
Yes, as long as it's an audio rate signal,
okay,
it won't complain. It'll do something. Like you can use K2A, which takes the control rate signal and interpolates into an audio rate signal. So that's a thing you can do. But you could also just take a nice clean line and then mess it up in some really weird way, but keep the audio rate, and it wouldn't give you that error message. Yeah. But okay. Yeah. Okay. So first what we're going to do is allocate an empty buffer for us to record into. We could overwrite fins, but why do that? Let's just make a new one. Let's see, we'll call this just tilde_b, I suppose. So instead of buffer.read, buffer.alloc, and we need to tell it the number of frames and the number of channels. So let's do a 5-second buffer. So that's how I like to do that, right? We need to give it the number of frames. So we just multiply seconds by sample rate, and that's what we get. And then we'll just do a mono buffer. Right? So there's that. Nice 5-second buffer. Nice empty space for us to work with. So that's all good. We'll say mic, sig. And so we're going to be skipping ahead just a little bit. We haven't really talked about hardware inputs and outputs. We've been using out. And so you might think in is going to work, right? Sure. If we look at the meters, in the default sort of situation here, we see that the indexing on the outputs and inputs are 0, 1, and 0, 1. And so, but actually what's going on behind the scenes is that all 4 of these audio buses and about 1,000 or so additional audio buses that are invisible behind the scenes are just indexed from 0 to the last index. And so actually this is bus 0, this is bus 1, and then with the inputs, this is actually bus 2, and this is bus 3. So we could say in.ar and then say I want bus 2 and 1 channel, and so that will actually give us this signal here. Or you can just use soundin.ar, and this is just a convenience UGen, which let's see if I can hone in on. It's all it does is well, I thought this would be a little bit. Yeah. Okay. So all it does is add the number of output buses. I think. Yeah. Channel offset. It knows how many output buses there are. And so chan offset is the number of output buses we have. And then it just adds that. So, okay, this is probably making things more confusing than it needs to be. If you say 0, it will give you input bus 0. So this is just maybe a little bit more intuitive. And before we get into BufRead, let me just, we're playing with fire a little bit here. And I did what wrong? I need to call this mic, right? So if I play this, I'm getting ready with command period here because we're just going to be passing my microphone signal. You know, I'll even turn down the faders a little bit. Why not? So hello, yes, you can hear my voice coming out of the speakers, and it's just a clean pass through, just to show you that we can. I'll hit command period on that. And in the recording, you're going to hear like some double speak because I've also got my voice going from the interface straight to the recording software. So you might hear a little bit of phasing here, but you know, I don't want to disable that and only rely on SuperCollider because I'm going to forget to turn it back on, and then we're going to have 30 minutes of lecture with no talking, and so I want to avoid that. So we've just pulled our signal in straight from our sound card, from our interface, and you know, we don't even really need, if we're just going to be recording, we don't need an output here, and we don't even really need sig. We can just say BufWrite will pass mic into B. We need to give it an audio rate index. So we'll just say line.ar from 0 to. Now I know I'm like sort of hard coding environment variables into the synth here, and you know, if we, you know, I guess we can be consistent here. We'll do it. -1 over BufDur. Done action 2. Do this there as well. Phase. Okay, and that's all we need. What I don't recommend you do, I mean, you should absolutely never do this. First of all, you don't need to, right? The point of BufRead is to just record samples into a buffer. And if you have a synth and that's its only job, it just doesn't need an output, right? You don't really need to be playing that. You could if you wanted to. But the other thing is, last I checked, the signal that actually gets output by BufRead is its phase input, which is this line that goes from 0 to, you know, 100,000 or something over the course of 5 seconds. That's just a very strange signal So probably you'll hear like a little pop, and then on the meters you'll see just solid red. So it's more disastrous things can happen, but don't do this. We're just building a synth-def, and its only job is to record into a buffer. So let's say buff B, and if I run this and just start talking into the microphone for 5 seconds or so, it'll be recording my voice, and then eventually the done action 2 will kick in, and let's see if that worked. Okay, that's looking very promising, and if I run this and just start talking into the microphone for 5 seconds or so, it'll be recording my. That's all we get. Okay. We could do phaser, and it would just overwrite, and we'd just get the latest 5 seconds whenever we stop. But so this is fine, and now we can, go grab this again. I don't even remember what this is, but we'll just say synth BufRd buff B, and I need to colon here. Yeah, so a buffer is a buffer. It doesn't matter what's in it. They're all kind of the same from the synth-def's perspective. So all the same rules apply here. I just wanted to kind of show you the basics of recording. And let's now, I think with maybe one of the last things we'll do with BufRd and BufWr is put them both in the same synth-def. You can be writing to and reading from the same buffer at the same time. In fact, you can have multiple processes reading from the same buffer and multiple processes writing to the same buffer at the same time. I really wouldn't recommend. I don't see a lot of benefit you can extract from having multiple processes writing to the same buffer at the same time, because they're either just overwriting each other if they're all using the same frame pointer, and so only the last one will end up in the buffer. Or if they're writing at different parts of the buffer, they're going to be constantly kind of overwriting each other, and that could be cool. I don't know. It's maybe worth trying, but it's much more common to have one writing process and then multiple reading processes. This is a nice way to create a kind of delay texture or something like that. Okay, so we'll keep a lot of this stuff. I am going to make an output signal here, and we'll use phaser. Actually, you know what? For the rate here, we've allocated this buffer on the server, so we're guaranteed that they're going to have the same sampling rate. So we can just say 1 here if we don't feel like doing buffer rate scale. And going from 0 to here, to the end. So that is our initial pointer. And there's our sound coming in. And then we're going to write the microphone signal to the buffer using this pointer. And then let's make phase R, which is going to be our reading pointer. And so we could make another phaser, but what I like to do here is take the initial phaser and just subtract some amount from it. Because we have our normal phaser, which is recording, going from 0 to, let's just for simplicity say 100, 0 to 100, 0 to 100. And we just want to subtract some information subtract a number, so that one is, quote, behind the other one. And then we want to use a modulo operation to wrap those values within the right range. Although, if I'm remembering correctly, you can give out of range phaser values to BufRd, and if loop is 1, which it is by default, it will automatically do the wrapping and modulo for you. So I think we don't even need to do the modulo operation. Oh, just as a side note here, this loop parameter sometimes confuses people because it's not quite the same as it is with PlayBuf. With PlayBuf, when loop is 1, it just automatically loops, right? But BufRd and BufWr are totally controlled by their pointer signal. So if you just give it a line that goes from 0 to the end over the duration of the buffer, and you set loop to 1, it's not going to loop, right? Because it's just a line. The line goes from here to here, done action 2, it's gone. Loop, in the case of BufRd and BufWr, only determines what to do when the phase values are either negative or beyond the end of the buffer. If it's 1, it will wrap them. If it's not, it will truncate them. Does that make sense? Yeah. So I usually just leave loop at 1 because it lets us just give it whatever values we want and it'll get wrapped. So we then want to say, okay, remember this is samples, right? And so if we want to make this half a second behind, we can say sample rate times half a second, right? And this is the number of samples in half a second. And then we're going to say sig equals buff read AR, 1 channel. We are going to be reading the same buffer, the same one we're writing to, and using our new read pointer. For safety, we'll do this to start. Make sure it's not too loud. I mean, I think it was fine. It was fine a second ago. I still am going to turn it down a little bit, not so much. OK, and the moment of truth. And before we do this, we're going to go ahead and 0 the buffer. Right? Wipe it clean. And we'll see if I've messed something up here. So I'm going to just run this and start talking, and you should hear a half-second delay in my voice. So if I, OK, nothing. Interesting. Yes?
We're calling the BufRd instead.
Yeah, there it is. Gosh, what would I do without you? OK, so I'm doing all this again just to be extra sure. And now we have a half-second delay on my voice. Not very exciting, I guess. It's just there are other ways to make a delay. You know, you can there's your various delay UGens, comb filters, delays with feedback. But with this BufRd, BufWrite, you know, maybe let's do something with multi-channel expansion and maybe taking some of the concepts from earlier in this lecture and kind of building them into a more complex delay layered effect. Yeah, thanks again for catching that mistake there. It's always something, isn't it? OK, so what do we want to change here? Let's do. We are going to instead of multiplying by a half second, we will do the array from. I don't think I ever showed this syntax, but if you do parentheses number dot dot number, it will automatically return an array, right, from there to there. If you can do something like this, and it will use that as an initial increment, 1, 3, 5, 7, etc. You can go backwards as well. Can't do this. You're never going to get to -5 that way. So anyway, so we'll start with the array 1 through 10, and we will lin exp them from 1 to 10 onto 0.8 to 3. Okay, so this gives us this array, and these are going to be second values subtracted from the initial pointer. So the first one's going to be 8 centiseconds behind, ascending exponentially to 3 seconds behind. So we're doing a kind of exponential delays in parallel here. And then we, of course, have to do this. And we don't really need this. So this is going to sound like this. Hello, 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 hello. Okay, so that's good. That's how you do that, right? And yeah, and they should be panning from left to right. Are they? I can't tell because of where I'm sitting, unless I've messed something up. Let's, because we are splaying, and so the quick ones should be on the left, and the long ones should be on the right. Okay. Yeah, so that's working as expected. That's working as expected. That's working as expected. Do this. Let's just copy what we had with that LF noise. All right, that sounded good. So we're adding, we'll do 10 for consistency. Noise generators. And deviating by 1/5 of a second in either direction. And again, scaled up to be measured in samples, not seconds. Here we go. Hello? 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 Okay, so there's some pitch variation. Oh, there's definitely some pitch variation. Should we really mess this up? We should like start making some arguments here. So we'll do this. There's definitely some pitch variation. And also the contents of the buffer. I should just stop that. The contents of the buffer remain. Command period does not mess with buffer contents whatsoever. But a buffer is just, if I didn't say this yesterday, it's just a block of memory that lives on the server that is basically globally accessible by any server process. Multiple things can be reading from buffer the same. It's just data stored on the server that's retrievable and overwritable by any number of processes. So just pressing command period wipes synth processes off the server and does a few other things, but it doesn't actually deallocate buffers or zero the contents, which is nice. That's really what we want. Okay, so we play this, and then we can say, oh, okay. So that's, we can start doing some really crazy stuff here. Might want to mess with this too, I guess. Okay, we'll do that. And then this. And then noise, hertz. Set that to 4. Hello? Hello? Yeah. Hello? Okay, let's do a sine wave because then we're actually going to be doing like FM stuff, but with sampling, with recorded samples, and which is kind of nice. This is another benefit of, you can do this with PlayBuf, but I think it makes more sense with BufRead. Okay, so noise hertz doesn't really make sense anymore. Say FM hertz and FM hertz. So we play this and then, hello? Oh yeah, let's make the range a little smaller. Yeah. Quite large for, that kind of sounds like FM, right? Hello? 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 That's fun. Anyway, the last chunk of chapter 4 is granular synthesis. And as I was writing this book, I thought, this really could be its own chapter. And, it's kind of its own category. But granular synthesis is so often deployed on sampled audio, and so many of the parameters are kind of the same. You give it a buffer, a number of channels, and you can use granular synthesis to kind of play back audio files so that they sound normal. But it's also possible to do lots of really strange things, separating duration from pitch and garbling a sound file and just kind of creating all these weird textures and stuff. So there's no granular synthesis on the homework that's currently assigned, but I would definitely like you to read at least 4.5, just through just 4.5.1, learning about GrainBuf, which is a really that's my usual go-to. There are others. There's T-Grains, and there's Warp 1, and these are all like kind of slightly differently designed granulators. But generally speaking, it's possible to get a specific sound with all three just by configuring the parameters correctly. But what I'd ask you to do is just read as much of the granular synthesis section as you find interesting, and bookmark anything that you like for possible final project down the road. Okay. Well, I think we're actually a little bit ahead on the syllabus. I kind of planned for one extra day of synthesis or sampling. So what we'll do next week is move on to sequencing. And so we'll be talking about streams, patterns, events, p-bind algorithmic, because what we've been doing so far is just making kind of a singular entity, a synth-def, which is some singular signal generating configuration or algorithm, and then we just make a synth, or maybe we make multiple synths or whatever, but we're not sort of aligning anything on a timeline. We're not sort of saying play this, then do this with this parameter, and then this and this and this, and making a nice sequence. And that's such an important part of music, because music is sound arranged in time. So that'll be the focus of our lecture next week, definitely the week after that, possibly 3 lectures, because there's a big library of sequencing tools in SuperCollider. And I think a proper explanation really begins, kind of with the basics and building up from that. I think it's good to have a really complete understanding of that. So you can look forward to that, and your sampling homework is due in a week. Stick around if you have questions, and I will see you next week.